So, welcome everyone. So, we are glad to be here to present you some research work that we've been doing on the electric vehicle chargers. So, it's been a joint work with Riccardo, which is with me, Alexandre Sazar, and I. We are all security researcher at Quarks Lab, and we did this research all together. So, what we are going to discuss today is what we call EVSE, so electric vehicle supply equipment, so all the devices that helps you charge your car. And the one that we are going to focus more today are the level 2, which are quite widespread, especially in Europe, and is being used both for domestic usage and also commercial usage. So this research has been done as part of our participation to the Points One Automotive 2025. And as part of this competition, there were a lot of devices that you could target. And the one we selected was the Hotel Maxi Charger AC, which was already present at the previous editions and for which we already bought the device. So what we can find in that device, so it can be used both for your home, but you can also find some of them in some parking lots. This is a connected device that is being used for especially OCPP for charging electricity for users. But you can see that the attack surface is quite large. You have USB, Ethernet, NFC, Wi-Fi, Bluetooth. So plenty of entry points if you want to do some security. All right, so first things first, what we wanted to do is to acquire the firmware to do some analysis. And so the device has basically two ways to fetch firmware, either directly through the Wi-Fi or through the Android applications and Bluetooth. And this is the later one that we are going to focus on. So we basically started reversing the Android application. Unfortunately, it's obfuscated with and spacked with SecNeo. But still, we were able to do some hooking with FRIDA. So at some point, we were able to basically find the DEXs into the memory. So we were able to dump them and reconstruct the application. So then we started reversing the application. We find some interesting endpoints that speaks about the OTA, over-the-air update. We were able to basically hook these functions to check what were the parameters that were being used. And if you're gentle enough, you send the right token, the right parameters, the serial numbers, and all these kind of things. And the hotel cloud gives you back a link that you can just fetch to then download the firmware. So yeah, we are happy with that. We have downloaded our firmware. Unfortunately, it were kind of encrypted, so we had to basically figure out what was really inside. So first things, we look at the entropy. It's quite low, quite diverse. So yeah, it's not that good. The byte distributions, we expect it to be like equal if it was purely random, but it was not. And we also use the tool that we developed at Quarks Lab to assess cryptographic primitive. And here we use the feature to assess PRNGs, and basically it failed almost all the tests. So yes, there is something fishy here, probably like non-safe cryptography. So the first thing that we wanted to do then is to try to find the key length that was used. And we assumed as a first guess that they were somehow repeating the key along the firmware to do the ciphering. So to do that, there is Charles Babbage and Friedrich Kaczynski, like 2 centuries ago, that had an approach to find the key length based off the GCD. The idea is the following, is that if you have repeating patterns, you can compute the distance between them. And if you compute the greatest common divisor between the distances, so here 60, 40, and 10, you should end up with something that is at least a multiple of the key length, if not the key length. And yeah, that's just to illustrate that. So we applied that approach, and we had some interesting matches, even though there were a lot of noise. And we had a good match on 256 bytes. But to be absolutely sure, we also used the index of coincidence that allows you to give an estimate of the key length. And here it was basically absolutely clear that the length was 256 bytes. So quite a large key. All right, so the pattern that we found that was repeating, we then assumed that it was made of zeros in the firmware, as we commonly find a lot of zeros in firmwares. And if you have 0 and you apply some simple operation with a key, what you end up, in fact, as a ciphertext is the key itself. So we basically try to take that repeating block and to apply it on the whole firmware with some operations to try to revert the operation that was taking place. And actually, it worked quite well. In the semi-deciphered, we obtained like lots of seemingly readable strings, like this one. This char set has already been seen. So what we can conclude from that is that it was not just a simple operation that was being performed, but something mixing maybe multiple of them. So at some point, we inferred that it might involve multiple operations and the different parts, a key made of 2 parts. And at some point, we just took out SMT solving to try to help us find the right combinations of operations and keys so that it matches. But there were a lot of candidates. So we went into refining our samples to do our non-plain text attack. And so we tried to find some more pairs of plain text and ciphertext. And so we also found AES's box in the firmware by doing a windowed search. You can see that it's a very noisy because, yeah, the deciphering was not, we don't have the good solution yet, but still we were able to find it. And so at some point, we were able to add more samples in our pairs. And here we only had 2 operations that stands out, adxor and subxor, which comes back to the same somehow. And we obtained even better strings here. We can recognize crypto things. So we kept going with that. And at some point here, you can see that we recognize what's a begin certificate tag, and with the line feed in the outputs. So we are clearly on some certificates. I mean, parts of certificates. We found multiple of them. And actually, what we can do here is just you can refine, add more constraints in your system, so that even though you don't know the exact value of the certificate in the plain text, you can at least enforce the character to match the base 64 encoding. So this is basically what we do. With SMT, it's pretty convenient. So we had even more constraints in the system. And here we obtain even better like strings, but still some fixes to be done. Yeah, you can see the exact same thing with the hexadecimal. And so but what we basically have done is that we refine the process a couple of times up until we managed to obtain a fully decrypted firmware with the XOR. It turns out the real algorithm is a bit different, but I will let that for questions, if any. So yes, we are happy with we have our decrypted firmware. Now we can start the vulnerability research on it. And I will let Riccardo take over.
Okay. Okay, so before diving into the firmware reverse engineering, let's have an overview over the hardware inside the device. So first of all, there is this control board that contains the main logic implemented by the manufacturer that is stored inside the STM32 microcontroller. On the right, you can see also an ESP32 that is used for Bluetooth and Wi-Fi connectivity. And on the bottom, an external flash storage. Then on here, there are also other peripherals that are exposed to the outside, like the Ethernet or USB-C. Then this board is connected over UART to the laptop TFT screen, and over the CAN bus to the power board, where there is another STM32 with another firmware that can be obtained with the same methodology that we just described. This board is connected directly to the connector that goes to the electric vehicle and to the electrical power line. In this case, it's a 3-phase. Then there is a NFC module and an LTE board for 4G connectivity that is also connected over UART. Now, most of our analysis focus on the control board because it's the most important one and plays the most critical role in the entire device. So by looking at the firmware, we realized that it was based on FreeRTOS. That is a well-known framework, and it was very useful also because we have an internal tool that we were able to use that leverages binary similarity to identify some of the functions on FreeRTOS in this case, and that was very useful to speed up the process of reverse engineering. Now, the other things to notice is that the firmware doesn't contain any kind of mitigations or protections like ASLR or stack canaries or everything. That makes the exploitation way more easy. So we were able in total to find 2 code execution chains, one over BLE that chains 2 vulnerabilities and the other one on the USB stack. So let's go first on the Bluetooth one. This is an overview on how the Bluetooth communication works. An attacker is sending BLE messages over to the Espresys firmware that is running on the SP32. And this chip is then translating all of these messages into 80 commands that is sending them over UART to the STM32. So the STM32 has to have a parser for all those 80 commands. It's important to notice that an attacker doesn't have control over the 80 commands themselves, with some exceptions. For example, it's able to send the read or write command, and with the write command that are respectively for receiving and sending data, and for with the write command it is able also to send arbitrary data as a payload. So the first vulnerability was in the BLE CFG parser. It's a simple stack-based buffer overflow. At the end of every 80 commands, there is this /r/n terminator for the string. And in this case, the parser is just scanning the whole buffer, searching for it, and then it's copying the content into a buffer located on the stack that is 8 bytes. And so it's easy to get a buffer overflow. There are only 2 notice here. First of all, the size is still limited to 100 bytes. So it's not arbitrarily long because it is enforced by the parser. And an attacker, as we said before, is not able to directly generate a BLE CFG command. So the goal now was to find a way of injecting this command. Now, the 80 commands typically are buffered because the communication with in the STM32 is asynchronous, and so the parser should account for that. Here on the right, you can see how the parser tries to understand which command has been received, and there is an order in which he analyzes the several commands received. Here there is a problem. Let's analyze this example where in one single payload you receive 2 commands, a read and then a write. And as you remember, the write contains a payload that is controlled by the attacker. So the parser is first going to check if there is an IPD command, but only at the beginning of the string in the first 8 bytes. It's not going to find it, so it's going to go over the next one. Then it's going to search for the write command, but only on the first 10 bytes. Since it's not there, it's still going to go over. Another function is called and it's doing basically the same, checking for the write. And at this point, since it didn't find it, the parser is quite sure that there is no write command. And so it's going to search for the next 80 commands in the whole buffer. That is 100 bytes long. So in this case, it's going to search for BLE con, BLE out, and then the BLE CFG And it's going to find it because it's part of the valid write payload that the attacker sent. So by sending these buffered commands with the arbitrary content with the BLE CFG we are able to trigger the vulnerability and the buffer overflow. Now, how do we exploit it? First of all, we need a place where to store the shellcode. By sending valid write command, we can the data that you are sending is allocated copied in a buffer on the heap, and the pointer to this buffer is stored at a known location in the data section in a variable that we're gonna call BLE TMP buff. So we have a way of storing the shellcode. Then we are gonna inject the BLE CFG command like shown before, and we are gonna trigger the buffer overflow. Now, you might question why we don't store the whole shellcode inside the stack since there is no ASLR. And that would work, but this was not reliable enough because there is still a little bit of non-determinism on the order in which tasks are created, and so where exactly the task, the stack ends up in memory. And we needed to be, we needed an exploit that was 100% reliable for Pontoon. So the other idea was to use a ROP chain, a return-oriented programming, but if you remember, the size of the overflow was limited to 100 bytes, and that's just as big as the stack frame. So we are just able to overwrite the return address. So we can only have a ROP chain with one gadget, not a lot of a chain. So, but we also have control over a lot of registers from R4 to R11. So the idea would be, in this case, to use a job instead of a ROP chain, a jump-oriented programming. What we have to do is very simple. We have to take the content of the BLE TMP buff that contains the address of our shellcode, put it in thumb mode, that means setting the least significant bit to 1, and then jumping over it. And we were able to do it with 3 gadgets. Let's see how it works. The first one is going to load the address from the data section. Then there is a junk instruction, and then going to the second one that is setting the thumb mode, adding 1 to the register R0, and then storing it into a scratch area that is an area in memory that we identified that was not used by anything else. Then there is another junk instruction, and then unfortunately this gadget is going to erase our address. But fortunately, we stored it before, so the third gadget is going to read it back and then branching over it. Now, these 3 gadgets are quite simple, but finding them took still a little bit of time, just because it was hard to find the 3 gadgets that were not overlapping on the register that were being used. So at this point, we have code execution with our shellcode, but we still didn't want to interrupt the service. We still wanted to restore the normal execution flow. So our idea was to divide the shellcode in 2 stages. The first one is going to create a new task using the xtask create free RTOS function, with the second stage as the actual address for the code. And then it's going to return to restore the normal execution flow. The free RTOS is then, the scheduler of free RTOS is going to execute the second stage. And so we have 100% stable code execution that is not going to impact the device. Now, I know what you're thinking. It didn't happen until you show a demo. So we do have a video recording on it. We are going to use ESP32 for delivering the payload. Here we are using to scan for the whole BLE devices. This is the one for hotel, and then we are going to attack it, sending the job chain, and the image is shown. For the USB vulnerability, I'm not going to go too much into details. It's very simple. In the setup packet for to the control endpoint, there is a W-length field, and there is no check over the value inside of this field, and so it's possible to get a buffer over read and overwrite depending on the request type. It's very simple. So now that we are able to get code execution, what can we actually do? Now it's important to know that since we were able to get code execution in the control board is also responsible for flashing the firmware of all the other MCU, of all the other components. So we are able to use the device full capabilities. We are able to move laterally in the whole device. But we still don't have persistency, so that's the first step. To achieve persistency across reboots, we can, since the external flash, the WinBond external flash is gonna have an encrypted version of the firmware that is used for over-the-air updates, we can just patch that encrypted firmware and just let the STM32 bootloader update itself. And that works. The only problem is that it's not persistent across updates, because the updates are gonna remove our implant from the firmware. So the other idea that we had was to directly put our implant in the bootloader of the STM32. The bootloader is not affected by over-the-air updates, so our implant will stay there forever. And there is around 40 kilobytes of space that is left unused for putting our implant. And with this, we get unlimited persistency. Now, let's see how to pivot then towards internal networks, external networks, or directly targeting directly the electric vehicle through the charger. So the device is used both by enterprises and domestic users, and so it's possible to redirect the attack to IoT devices like cameras or NAS, either through Wi-Fi or Bluetooth, since we can reuse the ESP32 module. Otherwise, we can also convert the EVSE itself into a botnet by reaching to a C2 server. And you might ask, okay, but a botnet of one device is not very useful. Well, fortunately, the Hotel mobile app is going to show the location of all the devices in the world. And that's nice. These are the ones that are in Paris. There are around 200 of them. And it shows the distance to each one of them. Does it remind of something? Well, we are gonna launch a new game, Hotel Go. You gotta find them and exploit them all. The other idea would be to attack the OCPP protocol, that is this protocol used between the EVSE and the central management server operated by Hotel. And there are several attacks scenarios that can be done. One is to steal the authentication info by users, by legitimate users, and then start a transaction by redirecting the billing towards them. And this is possible to get, it's possible to have free electricity with this. Otherwise, it's possible to redirect the attack towards the backend server. By having control over the power board, it's also possible to directly get free electricity, since there is we can remove all the checks in place in the power board. That's the one that is responsible for erogating power towards the connector. Or we can even redirect the attack towards the electric vehicle attached to the connector by sending invalid signals. And this can potentially harm the electric vehicle connected. So just to sum it up, I hope that through our analysis, it was clear that the EVSE is a critical bridge between internal and external networks, and it's bringing new interesting abusing scenarios like getting free electricity. At the bottom, you can see the 2 CVEs that we got for the vulnerabilities. And thank you. Now, if you have any questions. Yes. If you fail to decrypt the firmware, well, yes, like if you fail to decrypt the firmware, you either have to find a way to directly recover it from the internal flash of the STM32. That model was also vulnerable to some fault injection attack. That's something that we never tried, but that was a viable option in theory. Otherwise, if you don't get the firmware in any way, I guess your adventure ends there.
But you were having XOR and addition, and if it was a bit more convoluted, would you still be able to manipulate? So if the algorithm is yeah, that.
Yeah.
Can you hear me?
Test. Okay. Yeah, I really like how you tried to find the algorithm, but if it was a bit more convoluted, what would you do? Do you have other tooling in-house for more convoluted approaches?
No, it was very manual, and in fact, yes, if it was like a standard cryptographic algorithm, it would have been done. We would have failed, and if it was even more complex, it would have been way more difficult to get the plain firmware out of it here. But there would some people published approaches where they gather more firmware. We could also have tried to fetch previous versions to see if there is one that were already in plain text. Here the difficulty is that we only had the ciphered one, and we had to figure out what was the plain text underneath. So yeah, there's a question over there.
Quick question. So for the Bluetooth-based attack, did you have to pair to the device first in order to do that? And then in the public use ones, do they like using the app, do they expect you to be able to openly pair with the device so that you can leverage that attack?
Yes, there was a pairing, but in place, but there was no user input needed. Like you can just pair it automatically. It was using like the just work protocol, so that was not a problem.
Very cool.
I'm just asking question. Did you do that research just statical analysis, or you do some J-Link stuff, GDB server to like run that firmware in real life, or it was pure static analysis of firmware?
Yeah, this was a pure statical analysis. Yeah, I'm trying to recollect it, but no, like we didn't do any dynamic analysis. After finding the vulnerabilities, we were able to reflash the firmware of the STM32 and enabling the RDP0 mode, and so we were able to use a GDB to have a debugger, but only after finding the exploits.
Okay. You disabled RDP protection and then used regular ST-Link, like J-Link debugger to continue really development on the platform.
Yeah.
Thank you very much.
Okay.
Thank you.
Thank you very much.